In this chapter we shall deal with work and energy. In our daily life we do a lot of hard work, like, a girl is preparing for examinations, draws diagrams, taking online classes, boys discussing each other. Moms will say my children, working very hard. Does spending a lot of energy in studying hard involve any work? Now if we go by science, someone may be working hard, trying to push a huge rock. In fact, if rock displaces, work is said to be done. Here is a girl pulling a trolley, and another girl putting up a book from first rack to fourth rack. What is important is in both cases, force has been applied and displacement takes place. Hence, in order a work to be done, the following two conditions need to be satisfied. A force should act on an object, and the object must be displaced. So we now define work. Let a constant force, F, act on an object. Let the object be displaced through a distance s in the direction of the force. Let W be the work done. We define work to be equal to the product of the force and displacement. Work done equals force times displacement W equals F, S. If F equals 1 Newton and S equals 1 meter, then W equals 1 joules. Here we have an example of two kind of work. One is a boy pulling an object horizontally in the forward direction, resulting a forward displacement. This is positive work done. In another example, an archer shooting an arrow. We pull the string back by applying a force. As a result, arrow moves forward. Here work done on bow is W equals minus F into S equal to negative work done. One more example is a satellite revolving around the Earth. Here the satellite is under an inward force towards the Earth. But displacement taking place towards tangent means perpendicular to each other. Hence no work done is done. Let us cite some examples. Lifting an object up against gravity. Object moves up. Here force applied F and displacement h.is in the same direction. Hence positive work. But force of gravity acting vertically downwards. Opposite displacement. Hence negative work. We now take up the next example. A bullock is pulling a cart. There is a force on the cart and the cart has moved. So it's A plus I work done on the cart. Understanding work by a few examples. In case of negative work, the angle between the force and displacement is A. 0 degrees, B. 45 degrees, C. 90 degrees, D. 180 degrees. It is like this as angle between them will be 180 degrees, means D. A porter lifts a luggage of 15 kilograms from the ground and puts it on his head 1.5 meters above the ground. Calculate the work done by him on the luggage. Weight lifted M equals 15 kg, height lifted H equals 1.5 meters. So work done equals Fs equals mg. S equals 15 times 10 times 1.5 equals 225 joules. Let us see this video clip. A man is jogging early in the morning. That means working hard to lose extra energy. In another clip, a lady riding up the stony hill. Here again the lady working hard to release extra energy. With these examples we see that work and energy are related together. By the above example, we have seen that, if a body possesses energy, only then, is capable to do work. Let us try to understand it by taking some examples. An object alone is not capable of doing any work, but when raised to a certain height gets the capability to do work. When a raised hammer falls on a nail placed on a piece of wood, it drives the nail into the wood. When a children winding a toy car, chavi bharna, the toy is placed on the floor. It starts moving. When a footballer hit a ball, energy is transferred to the ball. And ball moves. Here ball receives energy and is transformed into work. Hence energy possessed by an object is thus measured in terms of its capacity of doing work. The SI unit of energy is joule, J, larger unit as kilojoule or kJ. Nature have provided us with various form of energy on earth such as light energy, heat energy, sound energy, electric energy, chemical energy, nuclear energy, mechanical energy and so on. Now let us have a block at rest, where energy is stored within the particle. We call it as potential energy, PA. Let us apply a force. Let acceleration and displacement produced as a ns. Therefore, work done. W is equal to force into displacement, that is, W equals MAS. That means an equivalent amount of energy was stored in the block when at rest. This is potential energy of the block. For a vertical fall, F equals mg, S equals h. Therefore formula for PA is equal to mgh. C unit of PA is joules. An object moving faster can do more work than object moving relatively slower. Objects in motion possess energy. We call this as kinetic energy. A speeding car, a flying aircraft, flowing water, a running athlete possess kinetic energy. It is the energy possessed by an object due to its motion. As speed increases, kinetic energy increases. Let a car is moving from A to B as shown. Can we find out an equation for kinetic energy and amount of work done of this car? Let initial and final velocity of car of mass m is un versus acceleration produced as a, distance covered is s, then v square equals u square plus 2as. Therefore, s equals v square minus u square upon 2a, s times a equals v square minus u square whole upon 2. But f equals ma. Therefore, a equals f upon m. Putting this value we get, s times f upon m equals v square minus u square whole upon 2, or fs equals m times v square minus u square whole upon 2. Hence w equals half mv square minus mu square, also called as work energy theorem. Hence work done is equal to change in kinetic energy. If car start from rest, that is, u equals 0, then w equals half mv square. The kinetic energy of an object of mass m moving with a velocity of 5 meters per second is 25 J. What will be its kinetic energy when its velocity is doubled? What will be its kinetic energy when its velocity is increased 3 times? Let W is work done, V equals 5 meters per second. W equals 25 J. W equals half m, 25, square. 25 equals half m, 25, square. Equation 1 stone. When velocity is doubled, W equals half m, 50, square. Equation 2nd, dividing 1 by second. 25 upon W equals 25 upon 50, square. Therefore, W equals 100 J.